Hello everyone, welcome to Physmatica. Let's quickly go through the most common type of functions. So basically from your high school years to your university and whatever you're going to study, you will face an algebraic or a transcendental functions. These two have a lot of subgroups, but the most important ones are the ones that are listed here, and we are going to quickly look through all of them. So let's just start by the algebraic functions. The most common type of an algebraic function is a polynomial. A polynomial is written in this form, but the best way to actually recognize a function and to know if it's a polynomial or not is to just take a look at all the powers of x, and if these n's were all whole numbers, then you are dealing with a polynomial. For example, x plus 2 is a polynomial, a quadratic function is a polynomial, a cubic function is a polynomial, or whatever you can think of. Just to be careful about, if you take a look at, for example, x to the power of minus 1 or x to the power of 1 over 2, these two are not polynomial because one of them have a different form and the other one, that goes to the power of 1 over 2, 1 over 2 is not a whole number, so it's not polynomial. But remember, both of them are algebraic functions, they're just not polynomials. So now let's take a look at the rational functions. A rational function is just two polynomials divided by each other. So basically p of x and q of x are both polynomials. Following the rules about polynomials, we just dividing them by each other, and as you can know, q of x cannot be 0. So let's take a look at a few examples. X plus 1 over x minus 1, or maybe a bit more complex function like this. The only point about a rational function is that because q of x is a polynomial, if you couldn't simplify everything to become a polynomial and you still had a division, you might end up with an asymptote. An asymptote is a very unique feature of them, gives you interesting graphs. So that's the only idea about rational functions that you have to be a bit more careful about. Now let's take a look at the irrational functions. This is the general form of an irrational function. Any function that you have that have some radicals in it is an irrational function, but there is an important fact here. So if you take a look at a square root of x plus 1 or 1 over a square root of x minus 6 or anything you can think of, the idea here is that if you used all your techniques and all your logics to simplify an irrational function and in the end you still ended up with some radicals, then you are dealing with an irrational function. Just take a look at this example. This looks like an irrational function, but you can actually simplify this and you get an x. So this is not an irrational function. That's the idea. If you try to simplify it and to get rid of all of the radicals and you couldn't, then that's an irrational function. Now let's take a look at the piecewise functions. Piecewise functions are the one that the rule just changes based on the input. For example, if you have x2 for negative x's and x for the non-negative x's, the idea here is that if I give you a number that is negative, you can only use it in x to the power of 2, and if I give you 0 or a positive number, you can only use it in the function x. So that's the idea. There's a lot of them. For example, absolute value is a common type of piecewise function. You have sign functions, you have floor functions, fraction part, which just gives you the decimal part of a function. So that's the idea, and these four are the most common type of the algebraic function. Now let's move on and go to a transcendental function. The first transcendental function is a trigonometric function. For example, sine x, cosine x. The best way to describe what is a transcendental function is this definition here. And algebraic functions are built from polynomials using operations like addition, multiplication, division, and root. So this is exactly what we did for the previous four groups that we just defined. We used addition, multiplications, divisions, and roots. Transcendental functions cannot be expressed using only those algebraic functions. So you cannot just define any transcendental function using those operations that we just used. These are completely unique functions. So based on this definition, all trigonometric functions are transcendental functions. Now let's take a look at the inverse trigonometric. Sine inverse, cosine inverse. An example would be secant inverse of secant x, tangent inverse of x, whatever you can think of. And one important factor here, which is very interesting, is that these trigonometric functions and the inverse of them are very restricted. So the reflection to the y equal x is how the graph for an inverse trigonometric function looks like. This is a very good idea when you are asked to draw a plot of the inverse trigonometric function. Makes everything much easier to understand. One other thing that I see a lot is that you need to notice that sine inverse x is not the same as 1 over sine x. One of these is an inverse trigonometric. The other one is just cosecant of x. So these two are not the same. Don't make that mistake. That's also one point I wanted to notice here. Now let's take a look at the other common type of transcendental functions. You have exponential and logarithmic functions. There's no need for me to give any example of this. Just you definitely know about them. They're very common. E to the power of x, logarithmic of x. And the idea here is that logarithmic functions and exponential functions are just inverse functions of each other. And if you just take a look at the transcendental functions, what we just discussed here, we had trigonometric and we had inverse of it. We have exponential, and then practically we have inverse function of it, which is the logarithmic. The idea here is that you have some unique functions, and when you do the inverse of them, you are getting these whole new properties that are also transcendental. That's the idea. And now for the last group, we have hyperbolic functions, which are very common in physics. Sine hyperbolic of x or cosine hyperbolic of x. An example would be, for example, this function or another function, whatever you can think of, exactly like a trigonometric function. And the idea is that hyperbolic functions are the complex number counterparts of the trigonometric functions. What does that mean? So you know that a trigonometric function has a connection to unit circle. You have a circle and you can actually define everything about a trigonometric function on that, the result that you get. So the idea here is that a hyperbolic function has a connection to unit hyperbola. So you're going from unit circle to unit hyperbola. So you're dealing with a completely different geometry. And this is very unique and very interesting. Hyperbolic functions have a lot of unique and interesting properties and makes them very interesting in some applications, especially in engineering. I hope you like this video. Thank you for watching and don't forget to like and subscribe. Goodbye.